Welcome back to Science Click. Today, the mathematics of general relativity, part 7, the Einstein equation. Our mathematical model is finished. On the one hand, we know how to describe a space-time geometry, its curvature, and to deduce how objects naturally move thanks to the geodesic equation. For this, we have developed a whole set of mathematical tools, such as the metric tensor, the Christoffel symbols, the Riemann curvature tensor, the Ricci tensor, and the Ricci scalar. On the other hand, we also know how to describe the energy content of the universe, and thus the bodies that it contains along with their motion, using a single tool, the energy momentum tensor. The most powerful idea in general relativity will be to equate these two notions. Using a single relation, we will write an equality between curvature and content. This equation, which reads as an equality between the geometry and the content of the universe, is called the Einstein equation. In our mathematical model, the Einstein equation is the only one that cannot be proven. It is inferred from observations, postulated because it describes very well the world around us. This equation contains all the predictive quality of general relativity. It allows us to directly relate the abstract mathematical model to concrete predictions about the universe. Usually, the Einstein equation takes the following form. All terms to the left of the equation represent the geometry of space-time. They involve the Ricci tensor, the Ricci scalar, and the metric tensor. The term to the right of the equation corresponds to the content. It is simply the energy momentum tensor multiplied by a certain constant which determines the intensity of gravity in the universe. This constant depends on the speed of light and on Newton's gravitational constant. It is chosen so that relativity is compatible with older theories and recovers Newtonian gravity when the pull is weak. It is important to understand that the Einstein equation is extremely hard to solve. As we saw previously, the Ricci tensor and the Ricci scalar, which appear on the left of the equation, contain complex calculations involving derivatives, sums, and products of the metric tensor. Moreover, the two sides of the equation are closely related. The content of the universe tells space-time how to bend, but conversely, the curvature of space-time dictates how objects move. Solving such an intricate problem on paper is almost impossible. In most cases, it is necessary to make approximations and computer simulations to solve such problems. In the Einstein equation, the curvature of spacetime is embodied by the Ricci tensor and the Ricci scalar, which is its contraction. But in a four-dimensional spacetime like ours, the equation has a very interesting symmetry. It remains valid if we swap the energy momentum tensor with the Ricci tensor and invert the gravitational constant. This new equation is completely equivalent, and we will see that in some cases, it can be easier to use. Einstein's equation is very complex, but it still accepts a number of exact solutions. The simplest and most practical is the following. Let us imagine an empty universe, in which we place a massive body of mass capital M. We suppose that it is spherical, static, that is to say that it does not evolve over time, and that it has no electric or magnetic properties. This body may represent a star like the Sun, or a planet like the Earth. Our goal is to determine the metric tensor, and therefore the geometry of space-time at a point outside the object. First, let's choose a coordinate system. we decide to observe the point from a very far distance, and we measure time on our clock, t, the distance between the point and the center of the body, r, and two angles, theta and phi. Our point sits in a vacuum. Therefore, the energy-momentum tensor is 0. Using the second version of Einstein's equation, we deduce that the Ricci tensor at this point must also be 0. To determine the metric from the Ricci tensor, the calculations are tedious and require solving multiple differential equations. But thanks to the symmetries that we postulated for the problem, it is still possible to obtain an exact expression. This is the Schwarzschild metric. The Schwarzschild metric depends on the mass of the object. If the mass is equal to 0, we recover the Minkowski metric, describing an empty spacetime. But around a body like the Earth, the Schwarzschild metric indicates that spacetime is curved. And the closer we get to the planet, the greater the curvature becomes. In the case of a planet, its surface prevents us from going too close to the center. And inside the planet, the Schwarzschild metric is no longer valid. But in the case of a sufficiently compact object, whose surface is very close to its center, we would be able to get close enough in order to reach a distance at which the temporal term of the metric with these coordinates is 0. We have reached a point of no return. Time is infinitely stretched compared to the outside. This is the Schwarzschild radius, the horizon of a black hole.